In this work example, we'll be looking at calculating the density of a thin cylinder. A coin is made in the shape of a thin cylinder as shown in figure 2.1. Figure 2.2 shows the measurements made in order to determine the density rho of the material used to make the coin. Calculate the density rho in kilograms per cubic meter. Density is mass per volume. So we're going to need to know the volume. They give us the mass, but they don't give us the mass in kilograms, it's in grams. And so we kind of can see a calculation we're going to need to do there. In general, the volume of some object, it's equal to the two-dimensional area times the third dimension. And the third dimension, we'll call it T, or thickness, all right? So what's the 2D area of this shape? It's going to be a circle, right? So we got the two-dimensional circle extended into the third dimension, T for third dimension, or thickness. So what's the area of a circle? Pi r squared. Multiply that by, you could call this h, and so some students may be sort of familiar with the area of a circle, pi r squared times the height, right? And so you'll see this as a familiar sort of volume of a cylinder equals pi r squared h. You can call this third dimension whatever you like, thickness, height, depth, whatever. In general, like this is true. All right, and so times the thickness. All right, and so we're going to calculate the volume here because we know that the diameter is 22.1. And so I like to calculate it like this. The volume of this coin is going to be the 2D area, pi. Now r, if the diameter is 22.1, then the radius is going to be 11.05 millimeters. For that, times the thickness, 2 millimeters. Now I've already dealt with the fact that I'm given the diameter and not the radius. Okay, so that's why I cut that in half, right? Half of 22.1 is 11.05. And milli is the same thing as 10 to the negative 3. And I've squared that because it's pi r squared. And I've got my third dimension and I've converted its millimeters into meters. And so now I'll have the volume in cubic meters. That's what I want the volume to be in. So I'll calculate that first. In my calculator, I've got pi times 11.05 by 10 to the 11.05 times 10 raised to the negative 3 squared times pi times 0.002, right? 2 by 10 to the negative 3, same thing as 0.002. I'm going to hit my engineering button. Okay. So I calculate the volume of that coin as 7.67 times 10 to the negative 7 cubic meters. I want the density in kilograms per cubic meter, so I need to convert the mass from grams to kilograms. So if density is mass per volume, and the mass is 9.6 grams, that's 0.0096 kilograms. And so I'm just dividing this by 1,000 because there's 1,000 grams in a kilo. So if I got something that's 9.6 grams, move the decimal point over 1, 2, 3 places. 0.0096 kilograms divided by 7.67 by 10 to the negative 7 meters cubed. So I get a density of 12,516. 0.3 if you want, but I imagine we'll have to clean up the precision to which we're reporting that answer. Let's see. So there they just sort of, they want to calculate the density, okay? Now calculate the percent uncertainty. Now state the value with its actual uncertainty. So that's a nice problem where it kind of goes through all the steps that we need to. Let's clean this up a bit. So here we just get a value that's like 12,516.3. And maybe you think to yourself, this isn't quite right. I shouldn't report it all the way out here. You know what? I'm going to round this. Let's just use an old rule of thumb. If it looks like there's only 2 significant digits in this mass, and this might be 3 and this might be 3, right? So it seems like 2 significant digits is all we should report our answer to. You look at that number and you might say, I don't know, 13,000. So maybe here you report the answer as 13,000, okay? Or maybe some students would call it 12,500, okay? We'll check the mark scheme and we'll see what would they sort of accept here, okay, for those 3 marks. But it's somewhere around that, right? That's the calculator value. I would avoid reporting a calculator value. That might be incorrect. Calculate the percent uncertainty in rho. So we'll remind ourselves that rho was calculated as mass per volume, and there was uncertainties and sort of lots of measurements that went into that. So we look up here. We can calculate the percent uncertainty from the mass was 0.5 gram of absolute uncertainty divided by 9.6 grams of measured value. So 0.5 divided by 9.6. If you want to convert both of these into kilograms, you can, but the units are just going to cancel anyway, so it doesn't really matter. 5.2% uncertainty from the mass. The thickness, 0.01 divided by 2 times 100%, so 0.5% from the thickness. And the diameter was actually measured to be this. So even though we used the radius, what did we actually measure in the laboratory was this value, right? So we still use that 0.1 divided by 22.1 times 100% is 0.45%. But remember, we used this and we squared it, right? So like we took this value and we halved it to make it the radius, but then we squared it. And so if there's 0.45% uncertainty in the diameter, there's the same 0.45% uncertainty in the radius. We do have to double it because it was radius squared. We remember how we calculated the volume, we had to square that radius. So I'm going to double my 0.45, so I got 0.9% uncertainty from the diameter plus 0.5% uncertainty from the thickness plus 5.2% uncertainty from the mass for a total percentage uncertainty of 6.6%. So 6.6% for that answer. If I go back to my calculator value of 12,516 and I multiply it by 6.6%, then I realize that the absolute uncertainty in my calculator, at least, is 826 points. Okay. So then I say, okay, that's the hundredths place. That's the hundredths place there. So I can rewrite this finally. Um, 12,500, right? Round it to the hundredths place, plus or minus 800. So you just sort of look at your basic rounding rules. Okay, this number is less than 5, so I round it down. The hundredths place is where my precision is. It's the place that I'm certain to, right? So, or you could think about it like this. It is the place where my uncertainty starts. Like I'm certain in the 10,000ths place, it's a 1. I'm certain in the thousandths place, it's a 2. I'm uncertain here. When I get to the hundreds, that's where I'm uncertain at. So I just round it to that, 12,500 plus or minus my rounded uncertainty at that place value. Okay. Here's where we find out if this works this time, where we change question paper to mark scheme. That's what we like to see. Clear all that. And okay, so they would have allowed 2 or more significant figures. Okay, 2 or more. That's very friendly. So you could have put 12,000. You could have put 13,000. That would have been 2 significant figures, right? So my answer of 13,000, they would have allowed it, because that does round to 13,000. But or more, you could have 5, because the question was really assessing your knowledge of this, like how do we deal with the correct way to report significance? At this point in the calculation, they didn't really care. I'm sorry, let me make it clear. All right, so this is the mark scheme for what we just did. And you can see the 6.6%, that's nice. And so we've done so many of these by now that it's like, you should feel pretty good about combining uncertainties. These are tough questions. It's always the case when you read the examiner's reports that more than half the students miss these uncertainties. And maybe it's because teachers don't spend a lot of time on it. It's like, that's not important, but I think it is. I think it's one of the ways to bring form to sort of something that even textbook authors sort of disagree about, which is, which digits are significant and how do we sort of count that up. This is the way we do it in physics. All right. Good work on that one. So then we had, I think, one more for practice here. 136, we get out at 144, 8 minutes. We go ahead and taking it over to the document camera. Let me go ahead and pause this video.